Hello everyone, my name is Zayan Ghosh. I am your physics educator. First of all, welcome to my channel, Quantum Pathway. In this channel, today I'm going to start a series of lecture on quantum mechanics, which will be very helpful for the students who are preparing for CSIR NET, GATE, JEST examinations. I will cover some most important topics on quantum mechanics. We can see the frequent questions from these topics, okay, in the different competitive examinations. Also, my lecture will be very useful for the student who is preparing for uh, PhD or integrated PhD interviews. So let's start. Okay, so you can see my name is Soyon. I qualified GATE with All India rank 262 and JEST with All India rank 12, and also I qualified CSIR NET. Okay, so today the topic is infinite square well potential. So you can see here this is the shape of infinite square well. So Moyle's potential. Why we call this infinity and why well? Okay, so you can see here this is the barrier. Okay, and this is also a barrier. Okay, a particle is here. So first we have to understand what is barrier. Okay, so let you are going in from one point, let's say A to B. Okay, and in front of you, when you are here, okay, then let's suppose in front of you you have uh, you have C a wall or let height of 1 meter. Okay, and so either you have to cross the wall to reach B or you have to jump over the wall to reach B. Okay, so this wall is called barrier. Now, here we used infinite. So when we called the wall is infinity, let this wall has height 1 meter and let another wall has height of 100 meter. Okay, so it is very easy to jump over the wall of 1 meter, but for you of height around 1 meter, let's 1 meter, let you have a height of 1 meter, then for you it is impossible to jump over the wall of 100 meter. Okay, or you cannot penetrate through this wall. Okay, to reach B. So for you, 1 meter is a finite barrier, but in the case of 100-meter wall, height wall, it is infinity for you. Okay. So infinity is relative, and this is the meanings of infinity. The height of the wall is so large that you cannot penetrate through this boundary, or you cannot penetrate through this wall, or you cannot jump over the wall. We have two walls at number one is at x equal to 0 and another one is at x equal to L. Okay, so if this is a particle, so the particle can go toward right, can go toward left, but when the particle reaches here, it cannot penetrate through the wall or it cannot jump over the wall. Okay, the particle is bound to x equal to 0 to x equal to L. In between, the particle will be found, always be found in between 0 to L. This is the meanings of infinite square well potential. Okay, now what the topics we will cover in this lecture. First, we will see the form of potential, how mathematically the previous slide, the figure can be represented mathematically. Then we will see how to write the Schrödinger equation or the form of the Schrödinger equation. Then we will see the solution of the Schrödinger equation, we will use some sort of techniques and we will obtain the solution of the Schrödinger equations, which will be the particle wave functions, and then we will draw the wave functions or the particle wave functions. So this is the barrier here. Okay, so this is the barrier. This is the barrier. Okay, so this region is x is greater than L, and this region is x is less than 0. Okay, so this is y-axis and this is x-axis. Okay, x-axis is represented as position, position coordinate, and y-axis as the potential. Okay, y-axis potential. So you can see that the potential less than 0 is infinite, potential in between 0 to L is 0, and potential greater than L is infinite. So the potential can be written as V of x, which is equal to 0 for 0 to L, for 0 less than x less than L. Okay, and infinity for x less than 0 and x greater than 0, for x less than 0 and x greater than. So this is the form of potential. Okay, this is the representation of potential. There are so many other forms are there. Like one can represent this potential as 0 for 0 less than x less than L and infinity otherwise. Otherwise. Okay, so there are several forms, but we will take this form and do the calculations. Okay, okay, and the particle must be there with energy E, which is greater than 0. Okay, the positive energy. Okay, so now the Schrödinger equation. So if you notice here that the potential V of x does not depends on time explicitly. That means it will follow the time independent Schrödinger equation. Okay, it will follow the time independent Schrödinger equation. Okay, independent Schrödinger equation. How it can be written? That is minus h cross square divided by twice m del x psi of x plus v of x psi of x is equal to e times of psi of x. So this is the mass of the particle. Okay, and this is nothing but the Laplacian, and del 2 del x2. This is the Laplacian operator. Psi is the wave function of the particle. Particle is the potential in which the particle is okay, and E is the energy of the particle, and is greater than 0. So this is the equation, or this is the Schrödinger equations. Now we will see the solutions, how it can be solved. So the time independent Schrödinger equation is written as 2 h cross minus h cross square divided by twice m del 2 psi of x del x2 plus v of x psi of x equal to e times of psi of x. So okay, now so we already told that the potential barrier is so large that if a particle reaches here, it cannot penetrate through the wall or it cannot jump over the wall. Okay, so the particle, the probability of finding the particle is less than x equal to 0 and greater than x equal to L. Okay, is 0. That means there is no probability of finding the particle in this region and also in this region. So particle will always be bound to x equal to 0 to x equal to L. Okay, that means psi outside the region. So psi of x, sorry, okay. So psi of x is equal to 0 for what is 0 for outside the world. Outside the world. Okay. Now we will calculate for this region, that is x equal in between 0 to L. That means for the region region 0 less than x less than L. We will calculate. So for x equal to 0 to L, the v of x is 0. V of x is 0 here. So Schrödinger equation become minus h cross square divided by twice m del 2 psi of x del x2 equal to e times psi of x. Okay, so simplifying, we will get del x2 plus 2me divided by h cross square psi of x, which is equal to 0. Okay, so this is the differential equation, which is a very popular equations. Let k, which is equal to root over of 2me divided by h cross square. Then this equation, the differential equation, become del 2 psi of x del x2 plus k square psi of x equal to 0. Okay, this is the solution. Sorry, differential equation become this. So we know the solution of this equation can be given as psi of x, which is equal to a times of sine kx plus b times of cos kx. Okay, so the solution can be written in this way. Okay, so now let's go to the next page. Okay, the solution we obtained, that psi of x, which is equal to a sine kx plus b cos kx. Okay, so we have some unknowns. We don't know about a, we don't know about b. These are constants, but we have no idea what is the value of a, what is the value of b. Okay, so uh, we have to calculate these things. So we have a boundary. We have one boundary at x equal to 0, other boundary at x equal to L. Okay, so we will use some boundary conditions. So boundary conditions, boundary conditions. Okay, so number one, we have one boundary at x equal to 0. For x equal to 0, psi of x equal to 0, because outside in this region there is a 0 probability of finding the particle. That means psi of x is 0 here. For the region x is less than 0. Similarly, there is no probability of finding the particle in the region, so psi of x equal to 0 here for x greater than L. That means at the boundary, the wave function as the wave function must be continuous, so at the boundary, the wave function must be zero for x equal to L, x equal to 0, and also the differentiation of the wave function, that means derivative of the wave function del psi del x at x equal to 0 should be 0. Similarly, number 2, at the boundary at x equal to L, x equal to L in the same way, psi of x at x equal to L is 0. Del psi del x at x equal to L must be 0 also. Okay, so we will use these boundary conditions to find out the solutions or find out the constants. So now apply the first boundary conditions. Okay, in the next page. So if we apply the first boundary conditions, that psi of x equal to 0 is 0, then we will get a times 0 plus b times 1 is equal to 0. That means b is equal to 0. Okay, so the wave function become psi of x, which is equal to a sine kx. Okay, now if we apply the second boundary condition, psi of x equal to L, which is equal to also 0. So a sine kl is 0. So either a is 0 or b is 0. Either a is 0 or b is 0. If we put a is 0, that if we put a is 0, then the wave function it's become 0 irrespective of the position. Irrespective of the position. That means the particle is here, but we are getting the size 0. That means there is no probability of finding the particle anywhere in the region from 0 to L, which is not possible. That means A cannot be 0. So what is 0? So sine KL is 0. That means KL is equal to n pi, because this is equal to sine n pi. For n is equal to 0, can be 0, plus minus 1, plus minus 2, plus minus 3, and all. Okay, now if we put n is equal to 0, okay, so this is some important phenomenon. If n is equal to 0, that means k is equal to 0. But we have k is equal to root over of 2m e divided by h cross square. Okay, n is equal to 0, k is 0. Okay, but we have this value as we have e, which has finite value, m, which has finite value, h cross, which has finite value. So h k cannot be 0. That means n cannot be 0. Similarly, k is equal to root over of 2m e divided by h cross square. It cannot be negative because m is positive, h cross is positive, e is positive. Okay, so k cannot be negative. So n cannot be negative. That means we are just left with k, which is equal to n pi divided by L, where n is equal to 1, 2, 3 positive integers. Positive, positive integers. Only the positive integers. Okay. Now, now the wave function becomes psi of x is equal to a times of sine n pi x divided by L, and n is equal to 1, 2, 3, the positive integers. Okay, now again we have another constant a. So we know that from the normalization condition is that from normalization, realize that a normalization condition from normalization condition, we know that minus infinity to infinity modulus of psi of x the square dx is equal to 1. What does mean? That means that the probability of finding the particle in the all region of all space is 1. Okay, here the wave function psi for the psi is equal to 0 for x less than 0 and psi is equal to 0 for x greater than L. Okay, so we can reduce that is minus infinity to 0 psi star psi dx plus integration of 0 to L psi star psi dx plus integration of L to infinity psi star psi dx equal to 1. This is 0, this is 0. So we are left with integration over 0 to L, and this is a square sine square n pi x divided by L and dx equal to 1. If we calculate this, we will get let's calculate a square divided by 2 integration of 0 to L 2 times of sine square n pi x divided by L into dx. So is equal to 1. Okay, is equal to 1. So okay, sorry, is equal to 1. Okay, this is equal to 1. That means a square divided by 2 integration over 0 to L 1 minus cos 2n pi x divided by L and dx. Okay, and dx equal to 1. So integration of this term will gives us 0. That means we are left with a square by 2 into L is equal to 1. That means a, which is equal to root over of 2 by L. Okay, so the wave function becomes psi of x, which is equal to root over of 2 by L sine n pi x by L. Okay, n is equal to 1, 2, 3. The positive integers. Positive integers. Positive integers. Okay, this is the solution of the Schrödinger equation. Now we have to know about the energy or the quantization of energy or energy eigenvalue. So to obtain the energy eigenvalue, we have the k. K is equal to root over of 2m e divided by h cross square, and also we get from the quantization that is n pi by L. So if we equate these two with by a square, we'll get n square pi square divided by L square, which is equal to 2me divided by h cross square. So from here we get e. Okay, n is equal to 1, 2, 3 or positive integers is equal to n square pi square h cross square divided by 2m L square, where n is equal to 1, 2, 3. So for let see something. For n is equal to 1, e is equal to pi square h cross square by 2m L square. Let this is E0. Okay, so plot here. So let's suppose this is E0. This line is E0. E0. Okay. Then n is equal to 2. We will get E is equal to 4 square. 2 square is 4. 4 is 0. Then 1 is 0, 2 is 0, 3 is 0, 4 is 0. Let this is 4 is 0. That is 4 is 0. Then for n is equal to 3, we'll get e is equal to 3 times 3 is 9 is 0. Okay. Then 9 is 0. Okay. So this is 4 is 0, 5 is 0, 6 is 0, 7 is 0, 8 is 0, 9 is 0. So you can see the gap between this ground state and fast excited state. This is the fast excited state. This is 9 is 0. Okay. So the gap between the ground state and fast excited is 3 is 0. And the gap between the fast excited state and the second excited state, which is around 5 is 0. Similarly, the gap will increase when we go for the higher and higher excited states. Okay. Now, now go for the visual representations of the wave functions. Okay. So for the ground state, n is equal to 1. Okay. That this is the wave functions written. Okay. This is the wave function. So n is equal to 1 is the ground state wave function, and uh, ground state wave function can be written as psi 1 of x, which is equal to root over of 2 by L, and sine pi x by L. And outside the 1, the wave function is 0. It is always. Okay. So in between the 0 to L. So plot it. So let's plot it. Okay. So this is x equal to 0, and let this is x equal to L. Okay. This is the position. This is the x-axis or the position. SLTI1 position axis, and this is the wave function. We are going to plot the wave function. Sorry. So we are going to plot the wave function, and this is psi of x. Okay. Okay. So if we put x equal to 0 here in this equation, if we put x equal to 0, the sine 0 is 0. That means wave function is 0 here. If we put x equal to L, that means pi, sine pi is also 0. Okay. So the wave function becomes 0 here, and also wave function becomes 0 at x equal to L. And now put x equal to L by 2. If we put x equal to L by 2, then x equal to L by 2, then we will get sine pi by 2. That means sine 90 degree, which will give sine 90 is 1. That means if here we will get a maximum, okay, which is the maximum value, and the value will be root over of 2 by L. So the wave function will looks like this. Okay. Okay. Now, if we plot the probability density, how the probability density varies with position of the particle, let's see. So, probability density is nothing but a P of x. There's a probability density changing with respect to time, with respect to position, which is psi mod square, and which is equal to 2 by L, and sine square pi x by N. Okay. So, if we plot the probability density, what we will get? This is the wave function psi of x, and this is the position of particle x. Okay, so this is x equal to 0, and let's suppose this is x equal to L. Both cases x equal to 0. If we put x equal to 0, the probability is 0. X equal to L, the probability is 0. In both cases, the probability is 0. But if we put x equal to pi by L by 2, L by 2, then the probability is maximum, and the value become 2 by L. This is the 2 by L. Okay, so it will looks like this way. Okay, so this will the probability density, that is psi mod square. Sorry, this is psi mod square, or the probability P of x. Okay, so it will looks like this way. Okay, so in the clear way, you can see here for X is less than 0, the wave function is 0. X is greater than 0, the wave function, X is greater than L, the wave function is 0. And it will follow sine curve for X equal to 0 to in between X equal to 0 and L. Similarly, the probable for the case of probability, X less than 0, the probability is 0, and also X greater than L, the probability is 0, but in between 0 to L, the probability will vary like sine square pi x by L. Okay, now go for the fast excited state. For fast excited state, n is equal to 2. Then wave function for the fast psi 2 of x, the fast excited state, is a fast excited state. The wave function can be written as 2 by L sine times of 2 pi x by L. Okay, the 2 pi x by L. And energy, what will be the energy? Energy is equal to 4 times of pi square h cross square divided by 2mL square. This is the wave function and energy. Okay, so if we want to plot this wave function, so this is the position x, and this is a wave function psi of x. Okay, this is the psi of x. Let this is x equal to 0. Okay, x equal to 0. Okay, so this is x equal to 0 here, and this is x equal to L here. If we put x equal to 0, that means the wave function is 0 here. If we put x equal to L, that is 2 pi is again 0. The wave function has two nodes at x equal to 0 and x equal to L always. Now if we put x equal to L by 2, if we put x equal to L by 2, x equal to L by 2, here if we put x equal to L by 2, there is sine pi. That means sine pi is also 0. That means here the pi is 0. So wave function is also 0 in between, also 0 at x equal to L by 2 in between 0 to L. Now let L by 4 and take another point L 3L by 4. Okay, L by 4 and 3L by 4. So if we take L by 4, that is sine pi by 2 pi into L by 4, which becomes sine pi by 2. That is the maximum. Okay, so at L by 2, there is here the positive maximum, and which is root over of 2 by L. Okay, so the wave function looks like this and this. For 3L by 4, if you put 3L by 4, that means 3L by 4, that is negative 1. Okay, 3L by 4 is negative 1. That means, so at 3L by 4, there is a negative value. So this is a negative minus root over of 2 by L. So wave function goes in this way and will looks like this. So the wave function will looks like this. If we plot the probability density, okay, if we plot the probability density, this is the probability density of two second excited state with respect to position. What will looks like? Then it will looks like x equal to 0, and this is x equal to L. And if this is the x equal to L by 2, then the probability density, it will just square. That means this will be just square. Okay, you have to square these wave functions. So if we square it, then it will become like that, and the value will be 2 by L. And also we have to square this, then the negative become positive. That means similarly it will goes like this. And this peak and this peak has the same height at the same height. So probability density will looks like this way for the second excited state. So you can see here in the similar way, x is less than 0, the wave function 0, and for x equal to 0 and L by 2, it will follow like this, and L by 2 to L, it will follow like this, and this is the minima here, this is 3L by 4, and this is the maxima at L by 4. Similarly, for the case of for the case of probability density, again this is L by 4. At L by 4, there is maxima. Also, there is a maxima at 3L by 4. Okay, and for x is less than 0, there is probability is 0. As x is greater than L, the probability of finding the particle is 0. Okay, Okay, this also the wave function is 0 for x is greater than L. Now, the derivative of wave function. This is a very important topic with respect to the I can say for the student who are preparing for the mm, interview. Why this is important? Because let's see. So let ground state wave function. So ground state wave function, we get that psi 1 of x, which is equal to root over of 2 by L, and sine pi x by L. Okay, this is the ground state wave function. Let make a derivative of this to d psi 1 of x over dx, which is equal to, we will get root over of 2 by L, and the sine derivative will give us cos pi x by L, and also there is pi by L. Okay, so pi by L, so pi by L root over of 2 by L, and cos times of pi x by L. Okay, so let's plot this. If we put x equal to 0 here, if we put x equal to 0 here, then the value become, the cos become 1, and the value will be pi by L root over of 2 by L. Okay, so okay, let's increase this. So at x equal to 0, the value is positive and the positive value is here. Okay, let do this. Now, if we put x equal to L by 2, okay, x equal to L by 2. For L by 2, there is cos pi by 2, cos 90 is 0. That means the value is 0 here. Okay, now if we put x equal to L, x equal to L, that means cos pi is negative 1. That means it will be somehow here. Okay, and this value is somehow pi by L root over of 2 by L, and this value is negative pi by L root over of 2 by L. Okay, sorry, 2 by L. So the plot will looks like more or like this will like this way, it will go this way, and it will go this way. But at the wave function is 0 here, at less than 0. For x less than 0, the wave function is 0. For x less than 0 and x greater than L, psi is 0. That means d psi dx is 0 in this region. So it will 0 in this region. There is so. So here you can see a sudden jump at x equal to 0, just the left of x equal to 0, just the left of x equal to 0, the value is 0 for d psi dx. And just at x equal to 0, so you can see here a discontinuity. Okay, you can see there is a discontinuity at the boundary, at the two boundaries. The function is 0 here. So the more clear way, okay, so here you can see for x equal to 0, okay, for x equal to 0, the wave function has a finite value. This part is not true. Okay, the plot will looks like this way. This is the correct. This is the correct image. So this is the correct. You have to follow my pencil. Okay. So the wave function is 0 for x less than 0, and it at x equal to 0, the value is we are getting a finite value. It is not 0 here for the derivative. Okay. For this derivative, the value is not 0, and it will follow the cos graph. And in the same way, for x equal to L, the value is minus root over 2 by L and by the L, and the 0 here. Okay, for x greater than L and x less than 0. For a realistic wave function or a physically acceptable wave function, psi should be continuous, and del psi del x also be continuous at the boundary. Both should be continuous at boundary. Okay, both should be continuous at boundary. But in this case, for the case of infinite square wave potential, psi is continuous, but del psi del x is not continuous. Why this is not continuous? Because the potential has an infinite jump. The potential at the boundary suddenly goes infinity. Only for this region, the derivative of the wave function become discontinuous and the wave function become non-realistic. Okay, so this is all about infinite squirrel potential, and thank you for watching the video.